Okay, this is the first video. It's general electricity. I'm going to talk about schematic, forming circuits, symbols, definitions, and then the three general electricity laws. So let's start with schematic symbols. Here are the most common that we'll have. And forgive me, I don't have a stylus, so it might be kind of sloppy. Okay, so let me just kind of say, excuse me, what's going on in this circuit. First, we have a battery, and a battery is just an electric potential difference. And what that means is there is a difference in electrons. There are a lot of electrons here, and there are not so many electrons up here. And so electrons will want to flow this way through these various different symbols to the red. Now the red is positive because it's lacking electrons, and the black part of this battery is negative. Now, excuse me, despite the fact that electrons flow from negative to positive, conventional current says that current flows from high potential to low potential, so from positive to negative. If you think about in relation to water, that makes sense, right? If I have a waterfall with water up here, there is a high potential for that water to fall down that ramp, and a low potential down here for that water to fall down the ramp. So it flows from high potential to low potential. So that's how I want you to think about current. Even though electrons are going from negative to positive, current is flowing this way. So what's going on? What are all of these different symbols? So let's kind of trace. It leaves the positive high potential terminal of the battery, and it goes through the squiggly called a resistor. Resistors resist current. The higher the resistor, the harder it is for current to flow through. We'll talk on the next slide about what makes good and bad resistors. The next thing it comes to is a capacitor. This is a parallel plate capacitor. Capacitors store charge. And so we'll talk about capacitance. And the more capacitance some capacitor has, the better it stores charge. Then we come through here and we go through a motor. If we're doing the snap circuits, the fan, the motor that powers a fan blade, that would be represented with this M. And it continues on, and it goes through this switch. Now, none of this current would happen, of course, unless that switch was closed. A switch is just a temporary break in the current. In the circuit. A switch is a temporary break in the circuit. So when you close the switch, circuit's complete. When the switch is open, there's a temporary break. And then we keep on going through this A, and that's called an ammeter. And you'll notice the ammeter is part of the circuit loop. All of the current that goes through this circuit has to go through the ammeter. We call that series. More on that in another video. Then you'll notice the one I skipped over here is the voltmeter. Voltmeter. Voltmeter measures voltage, and it's in parallel. And so, again, more on voltmeter and ammeter theory later. But these are the common symbols that you'll see in schematics, and you need to know what they are and what they do. So while we're on that note, let's talk about voltmeter, ammeter theory. So the voltmeter, I said, has to be done in parallel, and that means outside of the circuit, and it measures volts. Whereas an ammeter has to be done in series, and it measures current, which is amps or amperes. And so if I have a circuit here, if I want to measure the voltage at any point in the circuit, it's easy. I just take my voltmeter, and it has two probes, and I put those two probes somewhere around my circuit, and it'll tell me the amount of voltage between those two probes, the amount of potential difference between those two probes. Slightly more difficult if I'm dealing with an ammeter. If I want to measure the current in this circuit, I need to break apart my circuit, so break the wire, and add my ammeter into the circuit to where all of the current that flows through this circuit has to go through my ammeter. Here, not all of the, in the voltmeter side, not all of the current is going through the voltmeter. You can see at this point some goes that way and some goes that way. That's what makes it in parallel. Whereas again here in the ammeter, all of the current has to go through the ammeter. So when you want to measure current or amps, you use an ammeter and you put it in series. When you want to use a voltmeter, you're going to measure volts. To find voltage, you just stick your voltmeter somewhere in the circuit on whatever you're trying to find the voltage of. Now that brings us to our physical voltmeter. We have a multimeter, which means it's capable of doing both voltage, DC and AC voltage, current and ohms. So we have a V with a little squiggly, then a V with a solid line, then an A, and then an omega. And then we have a dial, and on those dials we have like 220, 200, that's 2000, 200, and then 2000, and then off. There's some other numbers, but these are the most important. When you're wanting to measure voltage, you need to stick the switch in the V with the line above it, because we're dealing with DC circuits in this course, and you need to turn your dial to 20 volts, because our circuits will never exceed 20 volts in this particular class. When you're wanting to measure current, or I, you set your multimeter to the A and to the 200 on the dial, because that's 200 milliamps. Now remember, that's milliamps, so you're going to need to move that decimal 3 places to the left to get amps, and you'll see why when we get to law calculations a little bit later. If you want to use a multimeter to find resistance, which is your omega, just turn it to the omega, and the only place on here to do ohms is, well, you can do it on all of these, but we will be doing the continuity test more than anything else in here. And that just lets me know if my current has a break or not. You can turn it to somewhere else with voltage, but remember there's a lot of different, you have kiloohms, you have just regular ohms, you have milliohms, so you have to really be mindful of where you have your dial set so that your decimal isn't in the wrong place. So that's how you use your multimeter. There's 2 probes. There's a black probe and a red probe. So make sure, excuse me, to make sure that you are using this correctly whenever you're asked to measure current, voltage, or resistance. So now the 3 laws that we're going to talk about. Ohm's law, V equals IR. Kirchhoff's Law 1, which is current is equal to the sum of currents. So current total, that is a hot mess. Current total is equal to the sum of currents in a junction. Kirchhoff's second law says that your applied voltage is equal to your voltage drops, so on and so forth. So what does that mean practically? Let's take a look at the 2 different circumstances here. Let's say that I have a loop. and I have a 3-volt battery and a 1 ohm resistor, I can use Ohm's law to calculate the missing variable, which is current. 3 equals I times 1, divide each side by 1, I know my total current is 3. Now, that's using Ohm's law to find 3 amps as my current. What also needs to realize is Kirchhoff's second rule. So let me do this in like red. Kirchhoff's second law says that the applied voltage has to equal the voltage across any resistor, or the sum of voltages across all your resistors. So I only have one resistor, so the voltage across that better be 3. And it is. My current is 3. My resistance is 1. 3 times 1 is 3. So there's 3 volts across that resistor. So all of my voltage is used up. Let's look at a slightly more complicated example. Let's say I give you that current is 3 amps. I'm sorry, current is 1 amp. And we can find this later in a different video, how I found that, but let's say current is 1 amp. So my applied voltage is 3. So that means the voltage across this resistor and the voltage across that resistor better add up to be 3. We'll call that V1 and that V2. So, again, Ohm's law, if my current is 1 and my resistance is 2, 2 times 1 is 2, so V1 is 2 volts. Do that same exact calculation. Current is 1, resistance is 1, V2 equals 1 volt. And wouldn't you know it, 2 volts plus 1 volts is 3 volts. So that's Kirchhoff's second law. The applied voltage has to equal the sum of the voltages of all of your resistors. So the final law is Kirchhoff's junction rule, so Kirchhoff's first law. And it basically says that current entering a junction has to equal the sum of basically all the paths of that junction. So say I have this junction point here that splits into 3 directions. We don't even need to know what happens at the end of those directions. Let's just say it does that. Say coming into this we have 4 amps of current. What Kirchhoff's law is saying is that's the total current. So I total is 4. It has to equal I1, I2, and I3 added together. So if I say that I1 is 2 amps, and excuse me, and I2 is 1 amp, you should know what I3 is based on this rule. 4 minus 2 minus 1 means I3 has to be 1 amp. And so that's Kirchhoff's third law. Your total current has to equal the sum of all the currents leaving that junction. So again, you'll see some more practical examples of Kirchhoff's and Ohm's law in the series Parallel and Complex videos. So if you have any questions, don't forget to ask.